Okay, welcome back to another calculus lecture. In today's video, what we're going to look at is another piece of information about the graph of a function that we can understand using the derivative. And in particular, what we're going to look at are the local and global extrema of a graph. And so you can think of extrema as sort of maximums or minimums, or maxima or minima. I think those are the correct plural versions of those words. Anyways, before we sort of dive right into this, maybe let's start with some definitions. So let's go ahead and define what we mean by these extrema. So definition, a point x equals a is a local maximum of f of x. So here I have a function f of x and a point x equals a, so just some particular value of x. This point is a local maximum if f of a is greater than or equal to f of x for all x near a. And near a is somewhat vague, but you can think of this as within a distance 1 of a, so 1 unit to the left or right of a, or 1/10 of a unit, or 1/100th of a unit, or something like this, just sort of locally around the point a. A is the biggest value of f of x, or f assumes its largest value at the point a. Likewise, x equals a is a local minimum if the reverse inequality holds. So if f of a is less than or equal to f of x for all x near a. Okay, so this is just the exact same thing, except now we're saying that f of a is the sort of lowest value that f assumes in this little neighborhood. And we're going to draw some pictures here in a moment. This is a formal definition which I want us to be aware of and to sort of understand, but really the picture is what's going to be, I think, more sort of informing our intuition. So that's what local maxima and local minima are. So maybe let's also define global maxima and minima. So let's see, x equals a is a global maximum if f of a is greater than f of x, not just for all x near a, but just for all x, period. Likewise, likewise, x equals a is a global minimum if f of a is less than or equal to f of x for all x. Okay, so global maxima and global minima are these points where f is assuming its absolute smallest or absolute largest value. Importantly, none of these points sort of need to exist. A function can have no sort of local or global extrema. Okay, so let's draw a couple of pictures here just to help inform our intuition. So we'll get a couple of axes going. And I'll draw two examples here. Okay, so let's say this is f of x and this is g of x. So g of x here has a local maximum at a, and it has a local minimum at B. So you can see that around these points, it's the absolute lowest value. It has this little dip or this little hump here. Okay, so, and likewise over here, we have a local max, but no local minimum, okay, or a global minimum for that matter. This is a local max and a global max, because if we assume the graph just sort of continues on down here, then this is the absolute largest value that f of x attains over all values of x. And this will be a local maximum and a global maximum, but there is no local minimum or global minimum. Over here for g of x, we have a local max and a local min, but we do not have a global max or a global minimum, okay? Because these are just going to continue off, and there's no absolute largest or absolute smallest value that g of x attains. So the definition up here is somewhat technical, and I include it because I want us to understand it, like I said, but what I really want us to know is sort of what, if I say what a local max, or if I talk about a local max, I want us to realize that I'm talking about this sort of shape in the graph. Okay, so all of that discussion to say local max, maxima and local minima are these sort of objects. Same thing with global max and global mins. Okay. So the next thing that we should, so we've introduced this concept about the graphs of functions. Now let's try to connect it to the derivative. So in order to do that, we need a little bit more definitions. So let's go ahead and write out another one of these. A little bit of a definition heavy lecture, but that's okay. So definition, a critical point of f of x is a point x equals a in the domain of f, so it's actually a point that I can plug in and evaluate the function at. It's like, it's, if my function is the square root of x, it's not a negative number. Those numbers aren't even in the domain of f of x. So at the points where I can actually evaluate f of x, this point is a critical point if, or such that, f prime of a, so the derivative at f is 0 or undefined. And the way to think about this is a critical point is a function where the tangent line is has a slope of 0 or infinity. That is, it's horizontal or it's vertical. So that is the tangent line is vertical, horizontal, or you can have these sort of weird situations where it doesn't even make sense to define the tangent line. These are very sort of strange examples, and we won't encounter any of them in this course, but we should say that as well, or is undefined. Actually, that's not even true. So maybe let's look at a couple of examples here. So I'll just draw sort of one big axis and put a few functions on it. So a point where the derivative is 0, so where we have a horizontal tangent line, is just one of these points, right? It's just, you have something like this, and the tangent line is perfectly horizontal at this point. Its slope is 0. You can also have something like this, where at a single point, if you were to construct the tangent line there, your tangent line would actually be vertical. Or you can have another case where you fail to be differentiable at a point, like the absolute value function. And the tangent line does not exist there because the derivative doesn't exist. Okay, so these are the sort of three cases where a critical point of f of x, we have the derivative is 0, or the derivative is undefined in one of these two ways, where the derivative simply doesn't exist because the limit doesn't exist, or the limit is equal to infinity. So the derivative would be like 1 divided by 0 or something like this when you evaluated the limit. That would give you a vertical tangent line. But sometimes, as we've seen in the written homework, you can have it where the derivative simply doesn't exist because the function is not differentiable there. So all of these points would be critical points of a function. So the main first thing that I want to say, so we have these local minima and local maxima, and this definition of a critical point. It may not be particularly surprising that the two are very much connected. So let's go ahead and state a theorem. We're not going to prove this theorem, but we'll just go ahead and state it. So if x equals a is a local extrema, so that is, it's a local max or a local min of f of x, then x equals a is a critical point. Of f of x. And one thing to note immediately is that the converse of this is not true. If we go back and look at this example that I just drew, we have two critical points here which do happen to be local max and local minimum, a local max and a local minimum, respectively. But we also have this point where we have a critical point, but there is no local max or local min here. So let's just be careful not to get that confused. If you are at one of these points, then you're definitely at a critical point, but the converse of that is not necessarily true, because you can have this sort of business happening. Okay? Maybe we'll do some specific examples with these functions. Okay? So if I'm at a local extrema, then I'm at a critical point. So what that means is that to find local extrema, it suffices to look at critical points. That is, points where the derivative is either 0 or undefined. So you can take this geometric sort of outlook or this geometric problem, and you can turn it into a completely mechanical, analytical sort of problem. So maybe let's see an example of that. So example. So find the critical points of f of x equals x squared. So we know what the graph of x squared looks like. Maybe we'll go ahead and draw that. So we know that x squared looks something like this. And what I want to do is find the critical points of this, and those will tell me all of the possible places where I can have a local extrema. Right? Local extrema can only occur at critical points, and so if I find all the critical points, then I've found all of the possible places where I can have a local extrema. They can't occur anywhere else. Not all of them may be local extrema, but it certainly gives me a complete list of candidates for where the local extrema happen. So let's find the critical points of f of x. Well, first thing we want to do is just differentiate f of x. So f prime of x is equal to 2x, and then we want to set that equal to 0, And if I set this equal to 0 and solve for x, then this tells me that x equals 0 is the only critical point of f of x. It's the only place where the derivative is equal to 0. And you can see that clearly from the graph of x squared. Okay? So the main takeaway again is that if I want to find these points where I have this sort of local max or local min, it suffices to simply compute the derivative and find where it's equal to 0 or where it's undefined. Okay? All right, maybe let's do one more example of finding critical points, and we'll do one where we find the critical points of a function where those critical points are points where the function is, or where the derivative is undefined. So find the critical points of f of x equals x to the, and we'll do 1/3. This is actually the graph of that function where I had the sort of S shape earlier. So just to reiterate, draw this graph again. The graph of x to the 1/3 actually looks like this. Okay, so this is f of x equals x to the 1/3. And we'll see in a moment why the tangent line is vertical at x equals 0. So f prime of x, we go ahead and compute that first. If I'm looking for critical points or looking to find local mins or local maxes, first thing I do always is compute a derivative. So f prime of x, apply the power rule, I get x, or 1/3, x to the negative 2/3. And I can write this as 1/3 x to the power of 2/3. And f prime of x, well, it's not 0 anywhere, but it's certainly undefined when x is equal to 0. So x equals 0 makes f prime of x undefined. So x equals 0 is the only critical point of f prime of x, and it's a point where the derivative, or where the tangent line happens to be vertical. The slope of the tangent line is infinity at that point. Okay, so critical points can be where the graph is has a local minimum. It can be where the tangent line is vertical, or it can be where the tangent line simply doesn't exist, as we had with like the absolute value of x at x equals 0. Okay, that sort of sharp V shape with the cutoff. All right, so that's everything for this video. The 2 videos from now, so the next video we're going to talk about another sort of feature of the shape of a graph, and after that we'll talk about, well, I found the critical points and maybe I can't look at the graph, maybe the graph is really complicated or I don't have access to graphing software. How do I actually classify these as local maxes or local mins? And we'll do that 2 videos from now using what's called the first derivative test or the second derivative test. But we'll see a little bit, we'll get a little bit of a lead into that tomorrow, or in tomorrow's lecture as well. All right, so have a good day, everybody.